Okay, right. Yeah, I'm Walter Brisken. I'm visiting from the National Radio Astronomy Observatory. And if you looked at the registrants, there are about 7 of us that plan to come from NRAO. So we represent a kind of a big group here. And one of us, Paul Demarest, couldn't make it, so I'm giving his talk for him. But I want to precede that with just a little description of other applications we're going to be looking at within the GPU context in the next few years. The NRAO operates currently 3 kind of world-class. One is the GBT, it's shown there on the left. It's one of the largest moving structures in the world, actually. We also operate the Very Large Array in Socorro, New Mexico, and the Very Long Baseline Array in crossing the whole continental U.S., including Hawaii and St. Croix. For the VLBA, we're currently undergoing a very large bandwidth upgrade, and we're aiming to use purely software correlation for the processing of the data to generate the visibilities that are then imaged. And presumably, these visibilities will be imaged in ways that are either conventional or using algorithms like the previous talk described. So we're hoping to eventually end up with a system that can process about 40 gigabits of data in real time. So GPUs are kind of a natural way to go for this. We haven't explored it in too much detail, so I'm not going to give you any performance numbers for that yet. The second application is with the Very Large Array. We're going to be significantly increasing the bandwidth in that project as well. And again, the need for GPUs might come in the post-processing when the astronomer himself will see upwards of 25 megabytes a second of raw data that they need to process and go through many, many iterations of the imaging to extract the full fidelity out of the data. So again, we might see GPUs as a way that the average astronomer affords a supercomputer on top or in his laptop so they can reduce data on their airplane ride to the conference. The thing I wanted to tell you most about today is the work that Paul Demarest is doing in Charlottesville. He's a pulsar observer. Is there a laser here? Some of you probably know that a pulsar is a very compact body here. This little white dot in the middle. It's basically the mass of the sun. It's compressed down to the size of New York City, and they can spin as fast as blenders. So they're the kind of extreme objects in astrophysics. They also have very strong magnetic field. When they rotate about different from the magnetic field axis, they produce a beam of radio emission, which once per rotation period may intersect the line of sight with the Earth. And when it does, you see a little blip in radio emission here. And you'll notice that pulse to pulse things look very different, but it turns out very nicely, if you average about 1,000 of these up, you form an average profile, which is very standard for every pulsar. Every pulsar has a different fingerprint, but the average over for a given pulsar remains constant with time. So this opens up the possibility of doing very high precision timing of pulsars to learn about astrophysics. And just at Princeton in 1993, Joe Taylor won the Nobel Prize doing just this. So pulsar timing is sort of a big business, and what you do is you have to form these folded pulse profiles. So this is what you get for one pulse period, but averaged using many, many individual pulses together. You do this both to form a kind of an invariant profile, but also to beat down your signal's noise. Sometimes you need tens or hundreds of thousands of individual pulses before you can even detect a single signature of the pulse. So the binning algorithms, these things, the binning is a little bit complicated because the Doppler shift of the Earth is changing with time, and if the pulsar is in an orbit with a companion, you have to fold the pulsar in a pulse synchronous manner, which is a tricky business to do and probably something that will be explored at some point on GPUs, but currently that's not the focus of the GPU attention. Just a little bit about why you want to time pulsars these days. The big thing is trying to detect gravitational waves. This would be another possible Nobel Prize in astrophysics, to directly verify that merging binary systems are producing these gravitational waves. And pulsars being so far away and providing this nice accurate time signal may be a way to detect these, sort of signals with periods of 1 to 10 years or so. So they're very long period signals that have that require systematics to be at the lowest possible level over tens of years. So when you do this pulse averaging, you have to worry about something called dispersion. When the pulse propagates across the galaxy, the free electrons in the ISM cause the different frequency components to arrive at different times. So you can see here these lines are roughly separated at a few megahertz, and the arrival time difference in neighboring frequency channels is more than the width of the pulse itself. So that means before you combine down to a single pulse averaged over all your frequencies, you have to shift this individual subcomponents, line them up, and then you can add them all together. This kind of has a problem because to do that properly, you need to make very fine frequency channels, which means that your time resolution has to go down by some amount. So if you have 1 megahertz channels, the finest time resolution you get is 1 microsecond, and we need to time these pulsars to better than 100 nanoseconds to do the science that needs to be done. So a technique called Coherent Dispersion was invented, and this has been invented a long time ago. And the idea is to, instead of looking at the total power signal, to look at the RF signal being recorded at the individual telescopes, apply a digital filter which backs out the dispersion. It's a very simple functional form, and the single parameter for that can be measured very accurately. So once you have your digital voltage as a function of time recorded at your telescope, you can put it through this inverse filter to recover an undispersed pulse, which you can then determine or measure to arbitrary time precision, or time precision that's restricted only by your bandwidth of your recording device. And you do this basically by doing a Fourier transform to a frequency domain, applying this phase rotation, which is different for every channel, and then inverse transforming back to time. And of course, you have a little bit of a overlap on each side, which is the width of the actual dispersion pulse within your band. The computational scale of this problem is kind of big. Depending on the frequency you're observing and the particular pulsar you're looking at, the transform size 30,000 to could be several million points. And you do this at full polarization, and the goal is to do this over 1 gigahertz wide band. So to put this in perspective, when I was a grad student doing pulsar stuff, I helped build a 5 megahertz bandwidth machine using specialized hardware, and this took one of the other graduate students a year or so to do, and a very expensive $100,000 machine. We want to increase that by a factor of 200, and that's in the course of 10 years, which is a pretty sizable increase. And GPUs seem to be a very nice way to go. The estimated need or performance is going to be about a half a teraflop, although this could easily be extended if you have if you're looking at globular clusters, for example, where you have one pointing of the telescope and you have 35 pulsars in that one field of view. You want to multiply your processing power by about that amount to do even better, to measure each of the pulsars independently at the same time. So Paul Demarest has done a little bit of exploration of these algorithms on GPUs. Using a basic algorithm, he was able to easily see a factor of 10 speed up for the larger FFT sizes. And again, like other talks have shown, that for small amounts of data, the performance increase is not as great as you hope, but you're usually not operating in these regimes when you're off to use the GPUs. I/O is still a big problem, and we think that if you do this folding algorithm inside the GPU itself, you can actually reduce the I/O by 80%. So this is something we want to look into. Also, we need to learn how to do I/O in parallel with the calculations, because once we do this, then I think I/O and calculations will perform or consume roughly equal amounts of time. So the folding might be a little bit complicated in the GPU because it's a little bit difficult to parallelize effectively. You have one accumulator vector, and you want to accumulate all the or data from all the other threads all at the same time, and the amount of operation per accumulator bin is very small, so you have a lot of loop overhead in that. And you're probably going to need double precision, which is going to obviously come in the next few years. So I think overall we're going to at least see a factor of 3 performance over this factor of 10 on top of the desktop PCs, and probably a box of a few graphics processors will be able to handle this 1 gigahertz bandwidth. Thanks.
Time for a few questions. Do you know if Paul, I'm looking at this accumulation. Do you know if Paul's looked into the atomic operations available on the newer cards?
I'm not sure if he has or not. I'll let him know. In the back, I guess.
I came down. I don't know if there's a way to ask questions about the series review. I'm just wondering if there's a different way, a fundamentally different way of implementing this on a GPU, like using, say, a small, like a finite impulse response filter type method, because isn't that effectively what you're doing with your FFTing and phase shifting? You're sort of shifting all of the samples along a little bit and then resampling them, right? So can you do a resampling operation which is much more efficient on a GPU that gets around some of the problems that you...
I don't know. The advantage of going into the Fourier transform domain to do the filtering is that you go with an in-log-in regime. I think if you stay in the time domain, you're stuck with n squared, maybe with a very small coefficient, but you still have that n squared, and that really hurts. I know that Paul is kind of interested in looking for faster algorithms to do this, and I don't think he's found anything yet. I should mention that both Paul and I are interested in getting email correspondence if anyone's interested in what we're doing.
That's a question. Maybe probably not even directly to you, but to all the radio astronomers in the audience. So I'm not a radio astronomer, but I get the feeling that a lot of your projects right now are computationally bound. So, for example, the MWA or LOFAR, if you had clusters 10 times bigger, you could, I don't know, have 10 times more beams or so. Is that, do I have the right impression?
I think that's at least half true. Some of it is that we build the hardware to be software bound in some sense, or we have artificial I/O limits set, like the EVLA correlator is going to be artificially throttled at 25 megabytes per second because we're not going to be able to consume the volumes of bits that come out of it. So I think we're as much storage bound as we're processor bound. Is that a reasonable thing, do you think?
Storage and I/O are both problems.
So will it be possible to enter radio astronomy collaboration by, saying we have a GPU cluster here that we can borrow you if we can do our beams in your telescope, something like that? Is that kind of the way where your field is going?
It could be. Well, the Allen Telescope Array is this telescope in California where the Paul Allen from Microsoft has been a big funder of that. And their idea is that you can have PI instruments that parasitically sit on, and they have a very wide field of view, and you can use whatever you want. You'd probably have to move your cluster to the antenna no matter what you're doing, because data rates, gigabits a second from out in the middle of nowhere where all these telescopes are is not an easy problem. Aside from that, and just kind of the logistics, I think that radio astronomy is up for these sorts of collaborations on a case-by-case basis.
Can I also ask the speaker to repeat the question, please?
Oh.